The purpose of this video is to demonstrate how simple it is to create a model within TSLOPE that can be used to analyze 3D slope stability. This example is from an open pit coal mine, and the surfaces used in the model were exported from the MapTech Vulcan model of the project. The default preferences are fine. Moving down the navigation tree, we can set the materials. Firstly, the overburden material, which is a laminated sandstone unit with strengths of 22 and a friction angle of 20 degrees. Secondly, the properties for the coal seam, the top of which acts as a bedding plane shear. This has the same strengths, just a lower friction angle of 15 degrees. Now we come to importing the surfaces. The top surface is the latest topography surface that was surveyed within the pit and includes the existing benches. In this case, it is a large file which can be reduced to improve performance. It is a simple process to decimate, and we will accept the recommended reduction percentage. Saving the new surface also adds it into the project, but we do not need to display both versions, so can switch display of the original large surface to off. Moving next to the basal surface, or potential failure surface. In this example, there are a series of 5 bounding faults in the roof of the coal seam that combine to create the potential failure surface. We import these in a similar way to the topography. We need to set the material for each basal surface. For the faults, it is the laminated sandstone unit. And for visibility, we can set opacity of each new surface to 80%. The 5th fault is imported from a cloud of points file. Note, you need to accept the points in the dialog box once loaded. Again, we set material and opacity for this surface. Finally, the seam roof, which comes in from a DXF file. For this surface, we set material to bedding plane shear. Because we can only select a single surface for basal during our slope analysis, we need to create a composite surface of these faults and seam roof. Tick to include the surfaces required. Note the yellow highlight showing which surfaces are included. To visually clip the surface data back to the area of interest, we can turn project clipping on. It should automatically snap to the top surface extents, though it can be adjusted using the nodes. Lock it again to hide the nodes. Lastly, back in surfaces, we can add the estimated groundwater surface as our phreatic surface. Now we are ready to define the slope case. Selecting the 3D slope case, we are presented with a dialog box. We can select the surfaces for top, basal, and phreatic, and it is a good idea to clamp the phreatic to top to avoid problems with our estimated groundwater surface extending above the topography. As simple as that, and a gridded model of the slope case is created. The columns involved in the stability analysis are shaded a darker color. In this case, there are a great number of columns outside the analysis, but using the slope clipping, we can trim the model down to a better fit. It is also possible to increase the number of columns in the grid. This will help reduce edge effects. Any changes must be applied before you can solve this scenario. Once solved, a Results tab will appear with the final results for the slope case. But the values at the base of each individual column can also be displayed graphically. You need to turn off display of the top and phreatic surface, and then you can select which data to display from within the data menu. As a comparison, we can create a 2D slope case. First, we need to define a cross-section line along a similar angle as the failure direction in our 3D slope case. Adding a 2D slope case, we are presented with a similar dialog box to the 3D, where we need to select the top, basal, and phreatic surfaces. Again, clamping phreatic to top. The section and slices are displayed. On Solve, we see the difference in results between a simple 2D approach and our 3D analysis.